Welcome to the banks of the Mississippi River for today's HEC-TV Live, The Science Behind the New Mississippi River Bridge. Hi everybody, I'm Tim Gore, your host for HEC-TV Live, and I'm very happy to welcome you to the construction site for this cable-stayed bridge that's being built just north of the Gateway Arch. Today you'll meet the construction workers, engineers, designers, and project managers who are bringing this bridge to life. What did it take to put those foundations into the river? How do you design a bridge to take into account barge traffic as well as car traffic above? Ask your questions by emailing us at live@hectv.org, and for interactive video conference viewers, we're going to get to your questions as well. Let's see what it takes to put that bridge into this river. So we've got this new bridge going up at the Mississippi River, and we've been joined by a variety of experts today who are going to begin to talk to us about it. And our first guest is Jeff Smith, who's the project manager and structural engineer with HNTB, which is the construction firm and engineering firm that's in charge of the whole thing. How is your relationship?
We were selected to design the bridge, to develop the parameters that went into what was needed to design the bridge. We took all the information, standard codes and things like that, things that we work with every day, and bring our knowledge to that and experience, and basically designed and drew up the plan set for MoDOT to use with their contractor.
And before we start talking about the bridge, you're a project manager for the project and you're a structural engineer. Give the kids some idea. What does that mean? What do you do on a daily basis? Is that a glorified title for?
People ask me that, and I did all the math and science in high school and in college, but day to day I mostly just write emails anymore, just making sure that information is flowing between the various parties and making sure everybody knows what they need to do their job. But we run computer programs that analyze the bridge, tell us how much force and stress are in the members. We use spreadsheets and things like that on a daily basis just to figure out how big members need to be in order to take the forces, which we'll talk about a little bit more. Mm-hmm. So it's a combination of working with math and computers and a lot of writing skills.
Oh, very cool. As we begin to look at some images of the bridge, because we've got a number of pictures we can bring up of the bridge and some video of the bridge as well. Let's talk about why the bridge is here. I mean, obviously St. Louis is a river city. Mm-hmm. There's a great many bridges that are also there, but why did we feel the need for an additional bridge, and why that location?
The primary existing bridge in St. Louis right now carries 3 interstates across it, so it's overloaded with traffic. There's a lot of traffic on, a lot of congestion, so in an effort to relieve that, it's probably been 20 years ago now, the community started coming together to determine, we need a new bridge, and where can we put that new bridge? One of the first things you really want to do in determining a bridge location is to figure out what you're trying to achieve. And in this case, we're trying to achieve taking that congestion off the Poplar Street Bridge, which we'll talk about a little bit later, but still connect the communities and connect the highways across the river. So that kind of narrows down your sites that are feasible.
Okay. Now we've got an animation we can also show which gives everybody an idea of what the bridge is going to look like in its final moment in time. This, of course, is where the construction is right now that you were just seeing, but we've got a wonderful animation which will show you what it will look like when it's done in its entirety and what it'd be like as you drive across the bridge from the Illinois side, the Missouri side, and vice versa. So you see the Gateway Arch just a little bit to the south. Now that direction is south if you're looking up screen, so to speak, and north would be the bottom of the screen. How much traffic is the bridge designed to take care of?
50,000 vehicles a day.
And what do you take into account when you think about designing a bridge? What are the parameters we need to care about?
Well, the first thing we look at is what we call dead load. And those are the components of the bridge that are always there, which what makes up the bridge, the steel and concrete. And we have a pretty good idea how much those things weigh, how much they're going to be. Those are some of the primary components. Then we look at live loads. Cars and trucks are obviously primary users of the bridge. We know how much a truck is supposed to weigh on a highway, but we don't know how many of those trucks are going to be on there at one point, if someone is going to be overloaded, things like that. So the factors of safety, the unknowns are a little higher there, so you put a little bit higher risk on those items. And then we get environmental factors: wind, rain, snow, ice, things like that. I always say, we'll design for a tornado and we'll design for an earthquake, but we won't design for a tornado and an earthquake at the same time, because that's just a too low of a probability. But on a major river bridge like this, you also have to take into account barge impacts, ice flows on the river. Loaded barge tow can weigh 60 million pounds, so that's quite a bit of a force to account for.
Yes.
In the design of your foundations, which we'll talk about later.
And in the next animation we'll show how it's in the process of being constructed. But the construction works from the banks to the middle, right? You're building the foundations, and then the piers go in, and then you're going to work toward the middle of the river with the roadway.
We will work toward the middle of the river. It's called a balanced cantilever type construction, and in this case, our piers are located near the riverbank, so we could span the entire river. And that's another consideration in your site selection. Is this the widest point of the river? Is the bridge going to have to be longer then? What are the soil conditions beneath the bridge? So you try to optimize those things in putting that together. But this bridge is being built balanced cantilever. Towers went up first, spent a long time getting those put up, and then they'll go out each side in a balanced fashion, kind of like a seesaw, from each tower back and forth with each piece until we meet in the middle.
Okay, so when you say the phrase balanced cantilever, what does that mean for the kids out there watching?
Well, a cantilever is something that would stick out one way from a wall or a pier or something like that. So we're balancing both sides of that. It's not touching yet, so it's connected. So when it's just sticking out unsupported from below, it's cantilevered out, and we're balancing back and forth. We can't build all one side of the bridge first or fall over.
Collapse would not be good. So there's all sorts of physics forces that work for you there. So how are you determining, like, what do you go through to determine this is the location for the pier? We want it to be this far from the bank, or that kind of thing, and how much space should be in the middle of the bridge?
In this particular case, with crossing the Mississippi River, the Coast Guard dictates how wide that channel needs to be for the barges and other river traffic. So there are safety concerns there. Obviously, we want to minimize the chances of getting hit by $60 million pound, so maybe $60 million too. So they'll dictate those, and based on the river geology and where the channel is, that kind of sets the width and the location within the channel. So that we just want to make sure that we're not creating an impedance to river traffic.
Now, there's all sorts of different ways you can build a bridge, obviously, but this is a cable-stayed bridge. Talk to the students a little bit as we look at some slides. We talk about the components of a cable-stayed bridge. What is a cable-stayed bridge, and why choose that option at this location?
Okay. Well, we talked about the span for this bridge is 1,500 feet, which is a pretty long way. It's the third longest bridge in the country that's built like this. So in order to do that, you want two things. Really. You want something that looks nice, and the cable stay bridge kind of meets that, and something that's efficient to build. And with today's technologies and today's materials, a cable stay for this span length really kind of makes the most sense. You wouldn't want to put, even if you could put a bunch of piers in the river, it's awfully difficult to put a pier in the river, and we'll talk more about that later. So better to put fewer piers and go up high, and then span with the cables. So the cables actually provide a support for each of these edge girder pieces, so they don't have to span the whole 1,500 feet by themselves. They're actually supported every 45 feet by one of these cables.
Okay. So the tower's going up, the cable's coming out, it's connecting to what would be the road pavement, what people would normally think about the bridge. And the amount of cables and the spacing of the cables is determined by physics forces, design forces? Like, do you actually have to deal with calculations like, because this is how much the bridge weighs, I need to have this many cables, that kind of thing?
Yeah, absolutely. And that's kind of a balancing point too, is how many cables do you want? If you have fewer cables, you're going to need more. So what's the balance point for something that looks nice and is easy to build? Each one of these cables has between 31 and 73 of these strands, which each hold 50,000 pounds.
Okay, so you're saying a cable has between 31 and 73 of these things in it?
Right.
Okay.
Right.
Wow.
And that's the steel. That's the steel. I don't know if this show up very well, but this has a plastic sheathing on it, which will help protect it from corrosion, so it'll last for 7,500, 125 years. So
this then is the plastic sheeting that goes over what's in my other hand, as I'm attempting to balance them out in a way that makes everybody see. Cool.
Right. And then those 31 to 73 strands will be encapsulated in what we call the stay pipe.
Okay.
Which is this really just the same kind of plastic that you'd use in a drinking cup, but there's some additives additives added to it so that it'll weather well and last a long time. But it's just plastic. And so this adds another layer of protection. This doesn't carry any load, any forces, but it further protects the strands so that they won't corrode.
I'll tap it just so you guys can hear what that's like. It is plastic indeed. At one point in time, they look very like concrete from a distance, but that would of course increase your weight immensely.
Yeah. Yeah, they're just plastic. You can add different. We have a white coloring on this for appearance, and also it decreases the heat up in the sun, which can also induce some weathering.
Okay.
So.
Well, we want to go to some student questions. We're going to go to our interactive groups in a minute. I've got an email question that's come from Mr. Miller. Thanks very much, Mr. Miller, that will help us with location. And then the first student group I'm going to go to is in Ohio, so don't unmute yet, Ohio. The question is, will access to the Poplar Bridge be cut off for one of those interstates, or will all the interstates that exist in St. Louis still go through the Poplar and only 70 go across that bridge? How does it work?
There will be some reconfiguration at the Poplar Street Bridge if you're familiar with it. One of the ramps will be removed, but otherwise all the access will still continue there. It's just that and this I wish we had a map, but traffic coming from the west on Highway 70 in St. Louis won't have to go down and across.
Okay.
In fact, they won't be that movement. You won't be able to make.
Very good.
So you will have to cross the river there, but the other highways that currently cross the Poplar Street Bridge will continue to.
And it's the Poplar Street Bridge that folks are seeing right now.
Right.
In case you're not from St. Louis, it just looks like a bridge. But for those of you who are, there's the lovely, using that term very loosely, Poplar Street Bridge. Let's go to our student groups to see what questions you have. Let's first of all go to Arts Academy, Canton, Ohio. A question for Mr. Smith.
You said the bridge you were building is the third largest in the country.
Yes.
What are the other two?
The two larger, there's one in Charleston, South Carolina, the Cooper River Bridge, which is 1,590 feet. And then the bridge a recent bridge just completed in New Orleans, which is about 1,530 feet.
Very cool. Thanks for that question, Arts Academy. Let's go all the way up now to the northwest part of America. Sandpoint, Alaska, a question from you. Unmute and come in and say hi.
How often do you have earthquakes?
Oh, you guys probably experience earthquakes quite frequently. Would I be right about that, Sandpoint?
Yeah.
That is a great question. That's actually something I'd forgotten to mention. But yeah, for those people not from the Missouri area, Missouri is one of the sites of one of the strongest earthquakes in history in the United States, the New Madrid earthquake in 1812, 1814. So while not frequent here, we can still have some very significant earthquakes. So that's another one of those design forces. So, like you said, we would design for an earthquake, but not at the same time as a tornado.
And do you actually design it so, I don't know, the bridge moves appropriately when the earthquake happens? It doesn't crack, it actually goes back and forth? How does that work?
There are different levels of criteria that we design for, and those are dictated in part by the owner and what they want to achieve and how vital this link is. Obviously, you don't want the bridge to fall down. So yeah, the bridge is designed to move. In a significant earthquake, there may be some damage, but it won't collapse. It'll still be open.
Okay, very cool. Great question. Thanks, Alaska. Let's now go to Wisconsin. Owen Withey Middle School. Owen Withey, if you guys are there, come in. What's your question?
How much money do you get paid to make the bridge?
Now there's a practical question. Well asked, Owen, Wisconsin.
How much do I get paid, or how much is a?
You can speak in generalities if you'd like, Jeff.
Oh, that's a great way out. Yeah, typically to design a bridge would cost 5 to 7% of the construction cost. The entire structure for this project was $230 million.
Okay. Oh, good, because he leaves you now with a math opportunity, so your teacher's very happy. Figure out the math and you'll know that answer. Let's go to Quail Valley Middle School down in Missouri City, Texas. Quail Valley, a question from you all.
How important are the supports to the bridge, the piers that go into the water? Would the bridge work without the supports?
We got some smart kids.
You like that, don't you?
This is great. You know, everything we build, bridges, roads, highways, buildings, everything rests on earth at some point. So the piers are very important. The bridge could not span the entire width of the river without the piers where they are. And at some point, you're going to have to touch down on land somewhere. So really, you know, it all starts from the bottom up. All right.
Very cool. That's a great question. We're going to have the chance to ask more questions throughout the program. Don't forget, if you're watching via the web or television, it's live at hectv.org. And that question from Quail Valley gives us a good transition to the next section of this program, which is all about building the foundation. So as we begin to talk about building the foundation, I want to give you some examples of other bridges that are in the St. Louis area that are very near this one. We've got a variety of video of different bridges, so you can see the different kinds of bridges that exist on the St. Louis city skyline that you would be crossing, because obviously a cable-stayed bridge is one kind of bridge, but when you saw the Poplar Street Bridge, it's a totally different kind of bridge. So let's go, for example, if we can, just to the footage of the Eads Bridge now. The Eads Bridge is a famous bridge, the first bridge across the Mississippi River. And what kind of bridge is this, Jeff?
That's a trussed arch bridge. If you guys have been watching the Men Who Built America on the History Channel, that's the bridge that's prominently featured with Andrew Carnegie standing in front of it. But it's Eads Bridge. It was built in 1871, longest span's 500 feet, and it was the first use of steel on a major structure.
Very cool. And the Eads Bridge, you may be familiar with its history, but this is the first bridge. We utilize caissons, which is similar to some of the construction techniques that we're going to talk about today. They had to get rid of the water, so to speak, to be able to build the bridge. But there were some significant injuries and deaths that occurred with the Eads Bridge because we didn't necessarily understand what was happening to people when they went that far down into the water, so to speak, that far down, and they came back up and they got the bends. So the Eads Bridge is a great bridge to do some history research about, to find out how it was designed and put together. And another bridge that exists here is what's known as the Martin Luther King Bridge. And the Martin Luther King Bridge, again, looks very, very different. And you're going to hear the voice of Randy Hitt now, who's the MRB Deputy Project Director for the project. And what kind of bridge is this, Randy?
This is a truss bridge, and that's a common bridge you've seen throughout the 20th century with the steel lattice work that you see there. And this is the more commonly, it can't span quite the distances. When you get the longest span, that's a suspension bridge. When you get to a shorter spans, like a simple span like you see an overpass, but the cable stay is the good medium between a truss and a suspension bridge.
Okay, so the type of bridge that's chosen for the location really depends then on the location, the amount of space you're going to have to cover, and whether or not you're crossing a large bridge or it's a small gorge or whatever the case may be.
Yeah, the span length, and so obviously you want to produce the most cost-effective. In this case, we got the cable stay, which is most cost-effective for the span distance of 1,500 feet that we had,
okay,
and it's the most economical, and it's a very beautiful bridge.
The last bridge we want to give you guys an example of right now is known as the MacArthur Bridge, which today is just a bridge for railway traffic. It looks different than with the bridge we just saw in terms of the MLK, but is this also a truss bridge?
It's also a truss bridge. There's different types of trusses that are designed, and this one has more spans, and not as long a span as the Martin Luther King, because have the heavier loads on it. But there's different types of trusses built throughout history.
So it's a variety of bridges that you're seeing along the St. Louis skyline, and obviously as you guys travel in whatever area you live in, you're probably seeing a wide variety of bridges as well. And there again, you see the footage of the Poplar Street Bridge, which is the most used bridge across the Mississippi River right here in the St. Louis area, and that's the bridge we're really trying to take a lot of traffic off of, that the new Mississippi River Bridge will accommodate. Randy, thanks for being with us today.
Well, thank you.
Give the students an idea about what it is you do with the project.
I'm the work for the Missouri Department of Transportation, and we have the oversight on the project, and we represent Missouri and Illinois since it spans between the two states. And so we coordinate, we hire the designers, work with them to make sure all the everything is incorporated in that we want in the project, and also administer the contract with the construction contractor. Let the contract and make sure all the materials are produced are quality, built in the right location, everything's tested as far as materials, make sure in the right location. The contractor makes sure, well, the important thing for them is make sure they get paid on time as incremental work and things like that. So day-to-day involvement, just overall management of the project.
And what we're going to begin to talk about now is the foundation. And that's exactly a reason I said it was a great segue from the question we just had from Quail Valley Middle School. As we talk about how you build the foundation, we're going to look at the idea of the geological surveys they do, how they test the foundation. So as we begin to look at your slides here, take us through, Randy, what are we talking about building the foundation? What are we noticing here?
The foundation for the two main towers is called a drilled shaft. And a drilled shaft is very commonly used on a lot of different type bridges, and it's just on a much larger scale for a Mississippi River Bridge, or the one that has a lot more weights and forces to deal with. The first part of that installation is a giant steel casing, which looks like a big steel pipe that's inserted down through the river into solid bedrock about 1 feet. And then at that point, when that steel casing is inserted, we remove all the mud and material. We got 50 to 70 foot of silt there from the river bottom that has to be removed. And that point on, we go down into solid bedrock at the bottom of the river. And in this case, we go 16 to 22 feet into solid rock. And these are 12 foot in diameter, so they're very large. And it's a long, tedious process to remove all that rock. Once it's all cleaned out, we'll set the reinforcing steel. Reinforcing steel is for the tension loads or the pull-apart loads, and concrete is for the compression loads. So all the reinforcing steel is installed at that point, and then it's poured full of concrete.
Okay, and what we're looking at here is some Missouri Department of Transportation video which deals with a test shaft that was drilled on the river, right?
Yes.
And just take the kids through the process here as we look at it. So your goal is what is that big concrete thing I'm seeing there?
What you're seeing there is actually the removal of the material. You see the big steel casing, and all the mud is pulled out of there and taken back out of the hole. Right here, the contractors are measuring to make sure what depth we are on the rock, and also to make sure it's clean at the bottom. That's a weighted tape there that you can bounce along the bottom. Here the workers are installing the giant, for all intents and purposes, big hydraulic jacks that sit on the bottom of this test shaft. The test shaft was installed and not a production shaft, so it was outside the footprint of but it was mainly to test the rock that goes into our assumptions that we made for the rock strengths. We wanted to verify those, so the contractor built a replica of the shaft with these giant hydraulic cylinders at the bottom, which would press up on the rock and verify the strengths. We went to 36,000 tons and did not fail it, which is a world record.
Wow. Wow. That's amazing. And here folks see a slide which is basically the same process happening, right? Those images of the test shaft.
Yes, you'll see on the left side there, you'll see the blue cylinders. That's the hydraulic jacks that went at the bottom. It's called a Osterberg cell test, or O-cell. And you'll see the workers verifying cleanliness before we poured the concrete on the right and making sure we're at the right elevation, and also the depth of concrete that we're going to be going to. And just some of the flushing out process in the bottom right corner there.
And then this diagram here, this is really great because I think we see both the schematic diagram as well as from above as you build the foundation, and we've actually got the concrete block going. Describe this for the students.
Yes, we have 6 drilled shafts at each one of these big towers. So the drilled shafts, as you can see here, go through the 50 to about roughly 30 foot of water in this location, 50 to 70 foot of mud and silt, and then we go 22 feet into solid bedrock there. And so to get started on that, you need the exact location. So a big steel template is set out in the middle of the river there and adjusted, and so you can see the openings there. You can see 3 of the cylinders, and you can see the openings for the other 3 that will go for these giant drilled shafts that go to the bottom. So that's to get your right location before you begin the work there.
That would probably be a good idea. Make sure we're drilling in the right place, obviously. We've got a question that's come via email from North Woods. Thanks very much for the question, because it leads back to, you talked about the foundations for the towers. Is there a reason the towers are pyramid shaped?
It was the most economical design, Tim. There was different types of cable stays. Some look like a gold post or an H pattern, and this is called delta shape, and that was the most economical to build and easiest for the contractor.
Very cool. And then how long is the bridge designed? This question comes from Victor, Montana. How long is this bridge designed to last?
They're designed for a 100-year design life. Now, we would hope that we would get more than that. Most of your structures, such as the Eads Bridge you've seen earlier, was built in 1874. But we want a minimum of a 100-year life out of it.
Oh, very cool. Let's begin to see student questions on this particular section. Let's go back up to Arts Academy in Canton, Ohio again. Canton, a question for Mr. Hitt about the foundations and pouring the foundations into the river?
How much does the bridge weigh in tons?
Oh, wow.
31 million tons.
Wow. I won't be lifting that anytime soon.
Let me clarify, 31 million pounds, not 31 million tons.
Doggone it. 31 million tons sounded amazing, though.
Yeah.
31 million pounds
That's still a lot of weight.
Enough.
That's still a lot of weight.
It's still a lot of weight that you have to deal with.
The reinforcing steel is about 8 million pounds, and the structural steel for the girder is about 15 million pounds. The rest is in concrete. So at over 31 million pounds, that's a tremendous amount of load that's got to be, what Jeff mentioned earlier, is dead load that has to be transmitted down to the bottom of these rock sockets. So all that load has to go through these 2 main towers. Right,
so the load is actually being transferred through those 2 main towers down into the bedrock below the river surface.
Yes, it is.
Wow, fascinating. And you're seeing the towers there in this image we've got. You're seeing some men working up there on the bridge surface itself As we look at this, we'll go to some additional questions from student groups, or back up to Alaska. Sandpoint, another question from you.
How is the bridge foundation tested?
The bridge foundation testing, we mentioned the test shaft earlier, but also tested as far as all the concrete and materials. The steel, reinforcing steel that goes into the bridge is tested in laboratories to make sure it has the right strength of the reinforcing steel. The concrete is tested on site and also in the laboratory to make sure it has the right strength and properties to it. We also want to verify before we pour the concrete down there it's very clean. That's what the guy with the weighted tape was, to verifying all that mud and silt was removed and that it was we didn't get any impurities in it that would reduce the strength of it.
Oh, very good question. Thanks, Alaska. Let's move back to Wisconsin again. Owen, a question from you.
When you guys build a bridge, like what's the most sturdy way that you guys build a bridge?
This is about one of the most sturdy bridges that you'll ever see. It's because, as Jeff mentioned, you're dealing with seismic designs. You're also dealing with wind load forces. The seismic was really what governed with all the different forces we have to deal with. This is a very stout bridge, and it's what we call a very heavy bridge. It has a lot of reinforcing steel in it that you would not typically have in a normal bridge that didn't have some of these forces. So designing for all these different things that are attributed to that really makes it a stout bridge, a heavy bridge. That's the reason you have massive amounts of reinforcing steel that you would not see in a typical bridge outside the seismic areas.
And what you're seeing in that image right there is the edge of the approach ramp from the Missouri side, and now you're seeing part of the bridge surface, and there you're seeing part of the very top of one of the piers, and then again the bridge surface. This is a good time to bring in an email question we got from Quail Valley. Thanks for this question. What kind of consideration is given to functionality versus aesthetics?
Functionality is the main driver of it, but you're always looking at the ways or aesthetics that can be incorporated in. For instance, on this bridge, we're going to actually paint the towers white at the end, and we're going to have uplighting on the towers and the cables, which will make it very visually stick out in the skyline. It's going to be a very beautiful bridge lit up at night. So that's one of the big attributes. Most of the great thing about a cable stay bridge is it's inherently just it looks like a modern architecture piece. And these towers are 400 feet in height above the water, so they'll be 2/3 the height of the St. Louis Arch, so it's going to really be prominent in the skyline.
Yeah, it's just gorgeous, and you see more of the footage going now as they continue to construct on it, and you see the amount of concrete that's poured there for that is the bottom of that foundation of the pier. Let's go. I've got an email question that comes from Elyria as we look at all this construction. We see the crane at work because it deals with, thanks Elyria, Ohio, this deals with safety precautions. So what kind of safety precautions do you guys go through in terms of construction workers, both in terms of safety of them as they work on it, as well as safety related ones for the passengers, so to speak, as they travel across the bridge?
A lot of the safety things that we look at here is very ingrained in the construction of this. Every person before they go on this site has to go through a safety training, and that would go for the engineers, the builders, everyone, the proper safety equipment. You're working out above the Mississippi River, so you have a life jacket on at all times when you're above the water. Going up heights, one of the things that when you're dealing with the 400 feet in height that is very important is cleanliness, to make sure that all the workers and everyone has everything cleaned up, because if you drop a nail or a small bolt off a ladder and hit you on the head, it may give you a little bruise, but when it comes from 400 feet, it could be deadly. So everything's very cleanly maintained. All the safety protocol, whether you got to be tied off when you're over 6 feet in the air with harnesses, things like that. So we have a safety boat on site at all times too, just in case we would have an incident where someone would go in the river, so they could be quickly retrieved and brought to safety.
Thanks very much for that question. Remember, everybody, if you're watching via the web or video conference or television, don't forget you can email us at live@hectv.org with your question. We're getting a lot of questions in, which is fantastic. If we don't get to all of them during the program, we'll send you email responses afterwards, so just keep sending them in. Let's continue now to talk a little bit about the shaft rock cores, the stuff you get out of the surface of the earth when you have to drill down and bring all of that bedrock up, as we talk about building the concrete and rebar shafts. And we've got some nice images for people as we look at some different PowerPoint slides in a minute. But this is video of a shaft rock core. This is bedrock that you guys brought up from beneath the Mississippi River, right?
Yes, it is. This is limestone rock that's the bottom of the Mississippi River, and it's buried below that 70 foot of silt we talked about earlier. And you can see the solid rock there, and that's very good, because a lot of times in the St. Louis area we have caves or fissures in the rock, and we were very blessed here. We didn't have a lot of these type of fissures or voids in the rock. So it was good solid bedrock which made a very nice foundation for our bridge.
Okay, let's go through some images so the students have a sense of how it is you go about building these concrete and rebar shafts that are going to create obviously the opportunity to hold the bridge up, that foundation. The first image talks about casing installation.
And here you see we talked about, it looks like a big steel pipe, and you put a casing or a casing installation as the first part because obviously you can't pour concrete out into open water. So this acts as a formwork for the drilled shaft and keeps the water on the outside, from the river water on the outside. And this is installed and also has some structural capacity with it too. It's a very thick steel. What you can see in this picture here is that doesn't look, maybe you can't get some sense of scale, but that's 90,000 pounds of steel in that big steel pipe casing. You can maybe see in the concrete counterweights of the crane in the foreground there, you can see a white hard hat of one of the workers there, just to give you some idea of how immense this is. So 90,000 pounds of steel just for the casing, which is hollow on the inside.
And as we go to the auger, which is what we see in the bottom left, is actually what's going to drill into the surface, right?
Yes, and that'll go down to the bottom and remove all the mud and nasty material that's at the bottom of the Mississippi River, which is taken out, and very efficient process, very easy to cut through, not too hard to drill through that. We did hit some old piling from an old, riverfront, probably from the late 1800s, early 1900s, that we had to go through, but it didn't pose much of a problem.
Okay, and as we go to the next issue, this is we're drilling in the core and we're actually retrieving stuff up.
Yeah, so once all the mud and silt's removed, then you got to get the rock out there. And this is what we call a core barrel bit. So it actually builds like when it cuts, it doesn't cut the full face of the rock. It cuts actually like a little channel all the way around the outside there. There's little bits that roll that have teeth on it. And the process is pretty slow. It goes about 1 foot per hour. And once you get to about a 6 foot depth there, then we have a device called a rock retrieval system on the right there, which fits over the top of that rock. It holds it in place with some hydraulic cylinders and snaps it off, and it's pulled to the surface and set on a barge, just much like the one we see in the last picture there. And all these are barged off to the side, and we actually repurposed these and used them for armoring for the bank on the Illinois side.
Oh, very good. And these shaft rock cores, this is what we saw the video of before. This is what you're bringing up.
This is what rock looks like at the bottom of the Mississippi River. And the big sections come out. We look for natural seams in the rock when we pull it up, so it's easy to break off. So that's really, you'll see some of those are a little bit shorter than others. About the maximum is about a 6 foot in depth. And just to give you some idea how heavy that is, one of those 6 foot pieces will be about 45,000 pounds.
Oh, wow. And obviously, to create this shaft, you've got to have the steel rebar before you're going to pour the concrete, and that's what we're seeing here.
Yes, once all the rock is removed, then the reinforcing steel has to be installed, and a contractor, the Massman Trailer Alberici joint venture, had a very unique process that they utilized on this. It was called the wind chime method. Normally you tie all this reinforcing steel on the ground and lift it to an upright position. They actually hung what we call vertical bars. The bar goes straight up and down from those yellow straps there, and those are hung up like a big giant wind chime you see on there on the left, and as it's lowered into the hole each foot, one of those round bars that you see there are lifted up into place and tied, and that keeps the bar spacing at the appropriate. There's actually 14 groups of bars that go vertically, and these particular bars are very huge. They are the size of a soda can in diameter and 13.5 pounds per lineal foot, and they're actually in groups of 3, so you're dealing with a tremendous amount of weight.
I would think. And now, of course, the big question, pouring concrete underwater, which I've always been fascinated by.
That's one of the questions we get a lot is, how do you pour concrete out in the middle of the Mississippi River? And a lot of people are very surprised that we actually pour it underwater. And so this diagram here shows you there's a giant steel tube called a trimmy that goes all the way to the bottom there. And so it's just clean water at the bottom, so you get a sudden rush of concrete that's pumped by a concrete pump truck down to the bottom, and that seals around the end of the tube. And as the concrete is continually pumped in, the water is pushed out the top, and the concrete is in the bottom. And concrete sets up very well underwater. It actually needs water to hydrate. And you can see in the diagram on the right, one of the contractor's personnel there is monitoring continually to make sure that that trimming tube is always inserted into the concrete, because if it pulls out, it's going to wash out the concrete and you'll have a big void there. So he's constantly monitoring the level of the concrete and the tube that's inserted in there, and what you see during this operation is the water coming out. And each one of these holds about 400 cubic yards of concrete, and we poured these at a rate of 100 cubic yards per hour. And a typical concrete truck hauls about 8 cubic yards, so it was a Very quick process, and it went very well, and we used special concrete mixes that flowed very well for this type of application.
Very cool. Let's go to some more student questions. Texas, I believe I left off with you. Let's go back to Quail Valley. A question from you.
How much does water pressure affect how you build the underwater portion of the bridge, and how do you accommodate for that extra variable?
Very good question. And what we do is on the water pressure there, like I mentioned, these drilled shafts are actually poured underwater, and there's a reason for that, because if you tried to pump out all the water inside that steel casing there, what would happen is you'd have a tremendous amount of pressure on the outside, especially at the bottom, and where that steel interfaces with the rock down there, you'll get a bunch of mud and silt want to blow in there, so all that pressure will want to be blowing into the inside the drilled shaft. So if you have the same level of water on the inside as the outside, it's always in balance, so you don't have to fight that water pressure and just use it to your advantage.
Let's go back up to Alaska. Another question from Sandpoint.
If there's a fissure or cave in the bedrock, how does the engineer deal with this?
I guess there's multiple ways it can be dealt with. Fortunately, on this particular project, we didn't have that instance come about, but some of the methods sometimes it's just a matter of you have to go a little bit deeper with the drilled shafts. Instead of 22 feet, you may have to go down till you get to solid rock, and so that adds a lot of cost to that. And so we'd prefer not to do that, but that is one option. Another is to go down there and just kind of like filling in some of those voids with a grout material. It's kind of like the filling a cavity of a tooth. You may have one little open spot down there, and so you inject that concrete to fill in some of those voids there, which makes it like solid rock.
Very good question, Sandpoint. And let's move into our other group. Let's go back to Owen, Wisconsin.
Yes, this question more or less relates to the career of an engineer. These 8th graders here still have a few years left of high school. What is something that they could be doing in high school to prepare themselves for a career in engineering?
Well, as we mentioned earlier, the math and science and physics are a very important part of this. You've got to have a lot of engineering calculations. You've got to look at reviewing a lot of, very intense calculations, especially when you get in the higher end of this bridge with the cable installation. It's something you'll use calculus and differential equations, things like that, some of the higher math, and of course geometry and those. But one thing I just really want to emphasize is the communication skills. Constantly on a project of this size and magnitude that you've got contractors, designers, material suppliers, all different agencies, environmental agencies, and people are constantly communicating, whether it be by email, by written letter, and so making sure that communication happens effectively, and because one small mistake in the communication can lead to millions of dollars in mistakes on a job site, so it's very important.
Thanks very much, and thanks for those questions. And Randy, thanks very much for joining us. We're going to give Randy a chance to switch out here. We're going to bring in our third guest, but as we do that, we want to show you some video of, again, the river location as we switch out, and go to a couple of email questions that have come in. And Tom, as we bring you in, I'll let you begin to answer these email questions so the folks at least have a sense of what you sound like before we begin to see you. One question comes from Hempfield School District in Landisville, Pennsylvania. Is there anything different in the foundation process if you're going into salt water as opposed to river water?
Well, there might be a difference in the concrete mix as far as the mix to allow the concrete to be more impervious to the salt water. Mm-hmm. So that would probably be one of the main things.
That's a great question, and don't forget, if you're watching us via the web or view-only video conference or television, email us at live@hectv.org. We're being joined now by Tom Tavernero, who's the project engineer for MTA, and let everybody know what it is you get to do.
Well, we interact with the field supervision and do the work planning for the temporary structures that are needed to build the bridge. They, for example, our Cofferdams, they have on the plans that there's footing 20 feet underwater, and then we get to figure out how to build a structure around that to build a permanent structure.
And that's what we want to go into as we begin to talk about Cofferdams, because I think it's really fascinating. You all probably have questions about this building underwater thing, and that's what we're going to begin to talk about. So cofferdam bracing, what's the purpose of a cofferdam? What does it do?
Okay, the purpose of the cofferdam is you build a box, and that allows you to seal the bottom of the box to prevent the water from coming up underneath of it, and that allows you to pump the water out and build your foundation in the dry.
So you're actually, what this is, this cofferdam installation, what you're going to be able to do now is build that foundation that we're seeing in the river?
That's right.
Okay, so the water's going away so men can actually work in that space.
That's right. So the process is we set the cofferdam bracing. This bracing, it's 60 feet wide, 100 feet long, and it's about 15 feet between the levels of the bracing. And this bracing weighs about 320,000 pounds. And so we had the cofferdam design based on the river level that we wanted to be able to work up to, so we could work at high water levels. And so these pieces were actually fabricated in Ohio into 100-foot sections and trucked to the job site. And we have a yard about 3 miles upriver, and they were assembled into the full size of the cofferdam, and then we loaded it on a barge and brought it down the site and picked it up and set it in place in one lift. So we were able, because we have the large capacity cranes on the site, we were able to do that as opposed to building it in pieces, assembling it in place out on the river.
Wow. Okay, now here we're actually looking down into the cofferdam, right? And we see men working. The river has been moved away.
That's right.
And that's concrete pour I'm seeing in the middle, right?
That's right. This is our leveling course pour. Once we set the bracing and drive the sheet pile, then we pour the concrete underwater, similar to what Randy described, a Tremy concrete pour. It's about 3,000 yards of concrete that goes into it. We pumped it over about an 18-hour period. And so once that concrete reaches a design strength, we're able to dewater the cofferdam, and you're left with the surface that kind of looks like the moon. You know, it's very, very wavy. And so we intentionally pour it a little low to where we can pour a slab on top and have a nice level pad to build the foundation on.
Okay, great.
So this is a shot of pouring the leveling slab, and you can see the drilled shafts. The casings have been cut away, and the concrete lowered down to the design elevation.
All right. And next, this is all the rebar steel that's going to go into this big block of cement foundation, right?
That's right.
And so, wow, how much is that? That's huge.
Well, there's about 1.4 million pounds of reinforcing steel on each footing. The footing's 20 feet thick, and it's 55 feet by 85 feet in planned dimension. But so there's this number 18 rebar. It's in bundles, so there's 2 bundles together, and they're basically on a grid, 2 foot on center. And so there are 7 layers of this of these mats, we call them, on the bottom, and then 5 on the top. So this is an idea of this weighs 13.6 pounds per foot. And to give you an idea, one bar across the short width of the footing weighs 750 pounds. So we spent quite a bit of time installing that, and one of the things as far as the design work we do, we design the temporary support. So the design engineer says you need to have the mats 2 feet on center vertically. Well, how do you support those? So we go in and design temporary supports. We had 100,000 pounds of just temporary support steel in each footing to support the reinforcing.
And so just so the kids have an idea, how much is this weighing that's basically I have in my hand?
13.6 pounds per foot.
We're going to get a little workout going as you work in with the rebar.
Yeah.
It's heavy stuff, and there's a lot of it, obviously, in the bridge. And our final slide gives us the idea of the foundation concrete pour. So the rebar's already there, and now we're pouring the cement into that location, right?
That's correct. Yeah, the footing's mass concrete, so we used a special mix. Normally you have cement is a primary component, but we had 70% of it. It was a blast furnace slag that acts kind of like cement, but the benefit of having so much of that in there is that it doesn't generate a lot of heat. And so one of the problems with one of the things you have to look at when you're pouring mass concrete is you don't want the center of the footing temperature to get more than about 40 degrees difference from the outside. So we had about 1.5 miles of cooling tube that we put in. Wow. It's a 3/4 inch polyethylene pipe, and so we put that on a 5-foot grid, and we pump river water through the pipes, and that allowed us to keep the difference in the temperature from the center to the outside within acceptable ranges. We had sensors put in the concrete so we can monitor the strength of the concrete, the temperature, and things like that when we were going through the process. So.
Wow, and this we're sitting with right here.
Right, this is just to give you an idea of how the sheet pile connects together. It's just like a knuckle and a hand that comes around, and so when we're putting the sheets in, these
and these are the sheets that are creating the space where people can work.
Right, that's what forms the cofferdam. The sheets are 80 feet long. They weigh about, a pair of these 80-foot sheets will weigh about 11,000 pounds. And so that's what we drive around the bracing to form the cofferdam.
Wow. Let's see what questions students have. Let's go to Alaska. Sandpoint, a question.
How do you get all the concrete?
Well, the concrete's supplied by a ready-mix company that's about 5 miles away from the job site. So they bring sand, cement, and aggregate into their plant, and they mix it up in a central mix plant, and then they'll deliver it by truck to the job site. It comes in trucks that carry about 9 cubic yards, or about 18 tons of concrete per truck. And so we dump the trucks into, a lot of times we've been pumping our concrete, so we'll dump them into a pump and we'll run it out a walk bridge through a 5-inch pipe, and that it gets deposited in the footing or the pier shaft. And here you see a video of, I believe this is a seal pour on the Illinois side.
Right, this is on the Illinois side of the river,
Right.
but there you see what the concrete trucks are bringing in. You see
That's
them
right.
putting the concrete in, and the process that's being used to do that. The concrete's coming from off-site. You're not creating it there. And speaking scientifically about concrete, because I know obviously concrete could have different, I don't know, textural elements or sloughabilities or those kinds of things. Right. What do you want the concrete to be like? Should it be the consistency of, I don't know, cake batter, or should it be the consistency of an omelet? What am I after for concrete?
Probably more like cake batter.
Okay.
I mean, they have tests we run where you put the concrete in a cone that's 12 inches tall, and you rod it down, and then you pull the cone off, and you measure how far it slumps. And so we like to have a concrete that if it's 12 inches, it would slump 10 inches.
Okay.
And so, you know, these days there's a lot of chemicals that we put in a concrete. So a concrete that has a real good consistency now is made with chemicals, and it's just as strong as back, you know, maybe 20 years ago. You used to have to get your slump with water, which would result in a weaker concrete.
So a lot like a brownie mix?
Similar to that, right.
Okay. Yeah, you know, I've imported a lot of concrete lately, but I do make brownies every once in a while. Let's go back then to Quail Valley Middle School. Quail Valley, another question from you.
Okay, so in the future, if you have a lot of traffic on the bridge and you want to convert it into 3 lanes each way, how would you reroute the traffic?
The plan that MoDOT has, and Randy could speak to this a little better than I, but the plan is if the traffic volumes dictate that they would build a sister bridge to the side. So there's not, I guess there's always a possibility that you could restripe, you know, right now the bridge has shoulders. You could take the shoulders away, and but that's the ultimate plan, is to, when the traffic conditions warrant, to build basically a twin to it.
Very cool. We've got a lot of email questions in. Northwoods wants to know, is there a regular periodic check that happens for those structures that are underwater for safety to make sure how the river's affecting them, that kind of thing? Are you checking it every year or whatever? Is there some sort of process that is used for that? Is that more of a Missouri Department of Transportation question?
Yeah, that's more of a MoDOT
I have a question. He's looking longingly over in the direction of Randy. Randy, come on in and just join us here. I'll let you stand right in front of the monitor here, and come right on in. And is there a process for that, for checking underwater safety and all that kind of thing?
Yes, there's something called scour. Anytime you put something in the waterway, the water increases speed around it and erodes below it. And so if you remove all that mud and silt, is it still going to stand? Actually, this here bridge is designed for what we call full scour. So even if all the mud in the Mississippi River suddenly disappears, the bridge will still stand. And we go through on other bridges where they're where there's more scour into, like that you've seen earlier. We go through and have dive teams and other people that check elevations, and you'll put giant, what's called riprap, or large rocks around there to protect those so that it won't erode down any further.
Okay.
But this particular bridge, the way it's designed, can go to full scour and not affect it.
Okay, good. We've got a variety of questions that have come in. So, and either one of you can speak to this, but I'll start with you, Tom. Mark Twain Elementary in Brentwood asks, so how does it meet in the middle? So like you're just continually connecting it together, and at some point it's kind of like the arch going up, at some point there's some piece that goes in at the end?
Well, we have, we erect 40-foot section on each side basically every 2 weeks. And then we put cables up in the panels and build a deck. Well, there's 7 different surveys that we take of the bridge through that process. So we're monitoring cable forces, the elevation, and the alignment of the bridge. And so we interact with we have a design engineer that has this the process established, and so we work with them and we make adjustments as we go. So the bridge, as you put it up, might vary a ½ inch here or there, and you make the adjustment as you're building to where they meet in the middle. Mm-hmm. And there's a special piece in the middle that with a few procedures we go through as far as making a closure to lock everything in. So.
Okay, and a different kind of question comes about, and Randy, you could probably speak to this, about the ramp approaches. You all are building the Missouri ramp approaches too, and obviously the Illinois Department of Transportation is building the Illinois approaches. And is the process similar in terms of like what we've seen? Obviously you're not dealing with water there, but in terms of the use of the rebar and the concrete, is the approach basically the same?
Yeah, a very similar process, and what we call simple span, where you just have a steel girder that spans from one pier to the next. And these are also founded on drilled shafts on the Missouri and Illinois side. But we do not have to put the Cofferdams and things like that since we're not working in the water. But it's a very efficient process. There's quite a bit of variance on the Missouri side. It's closer, rock is only 25 foot deep. On the Illinois side, where you got the floodplains, it's 90 foot to rock. But
okay.
It's the same process, and depending on what type of span, on the Illinois side, we had to go over railroad tracks, and so we had a little bit longer spans than we did on the Missouri side. Okay, let's go back to some student questions again. Sandpoint, Alaska, we just got 5 minutes left in the program. I'll just ask the question of you guys, Sandpoint, do you guys have a cable-stayed bridge up in your area, or are bridges in your area more of the truss bridge designs, or have you thought about it at all?
We don't have many bridges.
All right then you don't have to worry about that at all. Cool. It's really been great connecting with you, Alaska. Thanks so much for joining us. Let's go back to Texas. Quail Valley, your final question?
Where on the bridge do the most stresses and tensions occur, and how do you accommodate for those extra stresses in different parts of the bridge?
Oh, that's a great question. Thanks very much. Do you want to speak to that, or do you want to bring somebody else in? Or?
Well, Jeff could take care of it. I think one of the things, the highest cable force is in the longest stays. So our stays 800 feet long. They have about 2.3 million pounds of force in them. I think from stay to stay, the stresses in the girders are generally the same, although the anchorages are a little bit different. So I would say it'd be as you get out towards the center, you'd have that would be the highest concentration of stress. So.
Jeff, anything else you want to come on in and add to that? Come right on in and stand here near me about the monitor.
Okay, yeah, Tom's right. The cables there, the highest forces are in the center, the longest stays, because each stay is holding up the same. If you're doing your physics, each stay is holding up the same amount of vertical force, but it's laid out at a steeper angle. So in order to pull up that same vertical amount, you need a stronger force on a diagonal. And then all those forces from the cables are accumulating back in the girders.
Okay.
Putting those girders in compression, pushing them together. So the highest compression forces enter at the edge girders right at the towers, because everything's accumulating to those points.
Very good. Thanks for that. And Quail Valley, thank you very, very much for that question. We've just got about a minute and a half left, and so I just want to go to a question that we've gotten again from Elyria, Ohio, about effects on the river ecosystem. As you guys are working, for example, in the Cofferdam, are there any kind of environmental regulations you all have to concern yourselves with, or is there a part of the process that thinks ecologically?
Well, we have spill control plans and things like that naturally, but it really is it's a pretty minor impact on from the method of construction that we're using.
Great.
So.
Cool. Thanks for that question, Illyria. Thanks, everybody, for the questions that you brought to the program today. Tom, thanks very much for being here. Randy, Jeff, thank you guys for being here. The program will be archived on hectv.org in just about a week. We want to send a special thank you to the Gateway Arch Riverboat folks for all those great shots we got from the river of the bridge from the Tom Sawyer. If you guys in the St. Louis area, or you're visiting the St. Louis area, are interested in finding out about doing one of those cruises, you just go to coreofdiscovery.com and you'll find out all about that. We look forward to seeing you soon for another episode of HEC TV Live. Bye, everybody.